There is also a shortcut, Control L, but it doesn't work. Only this works. Yeah, everything else is okay. Here.
Okay.
You can go out.
Yeah.
Try it. No, the other one. And now you can't go back in.
Okay, I see.
So that you know, because it's your laptop.
I don't know.
Academic quarter.
Yeah, okay, welcome everyone, and also welcome our speaker, Mladen Pavicic. I think all of you have met him by now, and yeah, we're happy that he's around, and so we can already read the title of his talk so that we can learn a little bit about what he's working on. And I would like to take the opportunity to just say 2 sentences about him. So at present, he is a senior scientific advisor at the Photonics and Quantum Optics Research Unit of the Center of Excellence for Advanced Materials and Sensor at the Rudjer Boskovic Institute in Zagreb in Croatia. And so, as mentioned, he's been working a lot with the foundations of quantum mechanics, and already as a young researcher and postdoc, and then as a professor, he has spent many years in laboratories and in departments in Europe and in the USA. So as a Fulbright fellow, and also with the Alexander von Humboldt Foundation. And I think this is also what brought him maybe the first time to Berlin. So an Alexander von Humboldt fellowship, and at that time also working together with Harry Powell, so a very renowned figure in theoretical quantum optics and quantum photonics. And so since then, Mladen has been active in this field. In other words, maybe now it's called quantum information processing, but he has been working in quantum information before it was called quantum information, not to mention quantum technology. But so the field evolved, and a lot of activity is now called quantum information technology. But still, I think these foundations are very important. Yeah, so the idea of this stay and also of future stays and interaction would be to maybe develop some ideas and have a good collaboration between theory and experiment. And with the advance in quantum technology, more complex experiments and setups are now possible as compared to some things we discussed a couple of years ago. We had some work together and published some papers on quantum communication, but now I think there's also quite a progress in experiments, so more complicated setups are possible now. And that was also the idea, maybe to discuss what can be done now, or maybe in the near future, new ideas, what we can do with the setups that we use for quantum technology, but also using them for fundamentals of quantum physics. I think this is also very important thing we would like to do together with Mladen. And so today we hear part of it, what he's working on. Basically, it's about quantum contextuality.
Yes.
And I believe we are free to ask you questions.
Yeah, of course, you can interrupt me anytime you want.
Okay, great. So we're looking forward to a presentation and are happy to learn something about quantum contextuality. Yeah, thanks.
Okay. So it is quantum information more than quantum computation, I would say, although it's directly linked to that, as these 2 papers show. Actually, when you look at the error corrections, the quantum stabilizer operations with Pauli gates entail contextuality. So don't be scared of this graph. It's just a graph that was obtained by considering a particular error correction in that paper. So I would approach the whole problem step by step. When you look at the quantum contextuality, the most important part of it is the orthogonality between the states, and we can introduce them through the graphs or through the hypergraphs. As you can see, the same presentation of very simple contextual structure is much simpler in the hypergraph presentation, then in the graph presentation, and then as you go up with the number of edges within a hypergraph or graph, then hypergraph presentation is more and more favorable. So here you can see if you try to assign 1 to any one of these vertices in this hypergraph, you wouldn't be successful in this in a classical representation of quantum requests imposed on measurements. Because when you look at, for example, Stern-Gerlach device, then you have got 3 outputs and atom of spin 1 can go in any one of them. So you have always got such situation that you have got 1 ascribed to only one of the vertices because you have got only one detection of a single atom coming out of a Stern-Gerlach device. And also you assume that an atom must go out of the device, so you cannot have such a situation. So that's not allowed. And provided these 2 conditions are satisfied, you cannot assign 1 and zeros to such a structure so as to satisfy these conditions. That means they are contextual in that respect. If we remove one of the edges here, then you see that you can do that, and in that case the whole structure is classical and is called non-contextual. So here you actually need not have some particular state, so need not have vectors, and still we have to define dimensionality of the problem. And we define dimensionality of the problem according to the maximal number of vertices within each edge, and in that respect this is a 4-dimensional problem, that is 4-dimensional hypergraph. However, some 20 years ago, more than that actually, we realized that the general hypergraph couldn't generate contextual sets, and we introduced this MMP hypergraph, which is defined so as to satisfy in this respect first that every hyperedge must contain at least 2 and most n vertices. And when you look at this example, you can see that it's saturated, but it need not be. It can be that you can have less than n vertices in each of them. So the other part of the definition is that when you look at those edges that contribute to the contextuality, you cannot have, for example, in a structure, 3-dimensional structure minimal that you can have, you don't have such a hyperedge. And then a hyperedge may intersect in at most n-2 vertices. That means 2 3-dimensional edges cannot intersect, but in 4 dimensions you can have 4 minus 2, that is 2 vertices. And then to switch from the graphical representations to the computer manageable representation, we present these hypergraphs as strings. That means 3 vertices within a hyperedge would be written 1, 2, 3, or ABC, or whatever. And graphically, they are represented as on the first slide. So the main problem with the computation of these contextual hypergraphs is that the problem of finding states that satisfy this orthogonality condition between the vertices is a nonlinear problem. It's a simple problem with just 2 edges, for example, these 2. And we see that's a nonlinear problem, although when we make calculations, they are often polynomially complex, but in general they are exponentially complex in CPU time, and we'll see the consequences later on. So when you look at the main condition, for those who know what Kochen-Specker sets are, we have these two conditions that I stressed before as the main set of restrictions imposed on hypergraphs in our consideration. So what's important in contrast to the Kochen-Specker set is that we don't have to have coordinatization. We don't have to specify any vector or state we are dealing with. What's sufficient is just graphical or string presentation, and we can define contextuality just on the basis of assignment of 1 and 0 to vertices. And we don't know what vertices are. Vertices can be whatever. For example, in this example here, when they concluded that the stabilizer operations entail contextuality, they didn't deal with particular states. They only considered proper error correction code. What's important for the hyperedge presentation is that we were successful in reducing all existing contextual sets in the literature to the hypergraph presentation. So whether they were constructed from polytopes or Pauli operators or projectors or symmetries, it doesn't matter. They are all reducible to hypergraphs. So our algorithms deal with hypergraphs, and that's sufficient for elaboration of any kind of contextuality we can encounter. It consists in combining simple vector components so as to exhaust all possible collections of n mutually orthogonal n vectors. Now, here you see vectors appear. And while we can deal with hypergraphs without assigning vectors, we have also found an algorithm that, providing we have got simple vector components, we can generate in comparatively fast way all possible hypergraphs. That means all possible contextual sets for a given dimension. The procedure is the following. We assign vector components to vertices so as to form vectors which have to satisfy the orthogonality request within a hyperedge and the orthogonality request within the neighboring or intersecting hyperedge. And it's a pretty straightforward procedure, which is polynomially complex, so it's feasible, although it generates huge sets for dimensions that are bigger than 8. The main way to then generate all possible lower hypergraphs from such hypergraph master is to just remove hyperedges one by one and to check whether the resulting hypergraph is contextual or not. In that way, we have got a really numerous number of hypergraphs that are here presented numerically and here graphically. Here again numerically, and we see that when we go up to higher dimensions and the higher hypergraph sets, we have got more and more complicated and numerous sets. So that's, for example, for 6-dimensional hypergraphs, and this is for 8-dimensional hypergraphs. We also have got here 16-dimensional hypergraphs and 32-dimensional hypergraphs. So here we have got an example of the master sets we obtain. For example, we take as simple components as 0 plus 1 minus 1 and plus I minus I. And we get a master with 92 vertices and 185 hyperedges. Sorry?
Yeah, in this case, there you have like 0 plus 1 minus 1 plus I minus I.
These are vector components.
Yeah, but those are just general labels, right? It could be anything.
How do you mean that? General?
Like, those are like part of this huge alphabets that you construct. There is no real meaning for those.
No, these are for four-dimensional hypergraphs. And 0 plus 1 minus 1 means that one of the vectors that you can form from these components is, for example, of this kind, no? And then you can form all possible vectors from these components in this way. So that's the first component, second component, third component. Yeah? Is that the answer to your question?
Yeah, well, my question was more related because in the second line there you have an example where plus 1 is substituted to plus 3.
You mean this? Yeah, it's the same thing as here. You have got components, for example, 3 minus 1 plus I0 and so on. No?
Yeah, it's just to locate vector.
Yeah, yeah. And then you exhaust these vectors and you come to the set which contains one contextual. The first one is contextual, is 122 vertices and 212 hyperedges. The second one is non-contextual. It means you can assign 1 and 0 to all the hyperedges satisfying this request. And then in addition you have got 3 16-8 also non-contextual sets. These 5 sets are mutually unconnected. So there is no problem with dealing with this one separately. And then you can use this one to form such a distribution. Is that?
Yeah, I don't know, it's a little bit confused. Why the set with plus 3 have more solutions or more actions than the one with plus 1?
Because it's just a matter of orthogonal combinations of the vertices. We have got such forms of having more and more complicated structure. And when you impose this request and when you deal with MMP hyperedges, then these requests together with these splittings of more and more complicated hypergraphs gives you different number of hyperedges and different number of vertices. That's different from the standard hyperedges which don't have any restrictions, as for example that you should have mutual intersection of hyperedges up to n-2 vertices and so on. 0, 0, 0 is forbidden and such things. No? It's just a matter of combination of possible solutions to the request that the hypergraph should be contextual. That means that it should violate these basic 2 conditions. Okay? Here you have got an example of implementation in a lab of such a set. So you can see that if you deal with 0, 1, minus 1, I, minus I vectors, then you can represent such a hypergraph with linear and circular polarized photons. And it's also significant that you cannot represent it with just linear polarization. So although it's 2111, it is not a subset of the 2424, which is representable by means of 0, 1, minus 1. So it means that, again, this structure is intricate in the sense that it doesn't depend only on the number of the vertices and hyperedges, but also on these mutual connections. With this, we also come to the following point, and that means all these considered examples, including this one, assume that you have got n vertices within each hyperedge. That means you have got this, this, and this in a hyperedge occupied. But it's not necessarily so. You can have, for example, such a situation, which is experimentally not simpler, but it's simpler in calculation, because you don't have to deal with all the vertices. We'll see an example here, but what's the most important is the following. You can have such a generation up to 8-dimensional case, that means 3 qubits. Then you can jump to 4 qubits and 5 qubits, but anything in between is too complicated. And when you go to 9-dimensional case, it's not feasible. On a supercomputer, you just can't get anything out for months. In a parallel computing, nothing. So one of possible solutions that we found is to go not top to bottom, but from the bottom to the top. And that means that we can combine simple sets like this one, for example, or this one, to go up to 9-dimensional case without a problem, and then to 10-dimensional, 12, 14, and so on. The trick is that we combine lower dimensional hypergraphs into a higher dimensional hypergraph. And that means that we merge the vectors so as to satisfy orthogonalities. And in that way, we can go to whatever dimension we possibly want on a supercomputer, because the whole process doesn't scale with dimension. So we can go to dimension 64 or 100 or whatever, and we can have an application with the orbital angular momentum, no? Because already Zeilinger has shown that we can, in a lab, produce more than 100-dimensional orbital angular momentums, and orbital angular momentums are all orthogonal to each other. So we don't have this problem. The other thing is that we can go to so-called non-KS hypergraphs. Like this, where some of the vertices are missing from the hyperedge. We have to have them all when we set up the experiment, because, for example, in this Stern-Gerlach device, if we just don't look at 2 of the exits, we just have output probability of 1/3. And how we can establish that is because we measure these 2 other ports, and then we ignore them later on when we deal with numerical elaboration of hypergraphs. And so when we come back to our application, we'll take this into account. Our first application is that we simply make experiment which would confirm contextuality. Most of the experiments, 24 of them in the past and in the literature, were of this kind. But now we came to the stage that it's not any more important. We know what we'll get, so we should go to other kind of applications. Bechmann-Pasquinucci proposed quantum cryptography with larger alphabets, not only 0, 1, but also 2, 3, and so on. It doesn't make any difference in direct information, but it better eliminates an eavesdropper. So a possible application of hypergraph sets in this respect is unfortunately not a direct mapping of Bechmann-Pasquinucci proposal or even BB84 for the following reason. When we look at the contextual sets, we take into account this restriction that we cannot assign 0 to all vertices within a hyperedge, and that we have to assign 1 to one of them as a classical condition. And when we want to have a quantum application, these 2 conditions should be violated. But Eve need not take this into account. If can say, I don't care about this condition. I just send in the same way in which you'll get through a quantum experiment. Because, for example, in this way, you have got 1/3 of an outcome in each hyperage. No? It's 1/3. It's either here or here or here. No? And when you look at this thing, when you take out these vertices, this is now a contextual set, a contextual hypergraph. You can see that you cannot satisfy the 0, 1 condition. If you put 1 here, no, then 0 should be here and here, and if you put 1 here, 0 should be here and here, and these two things are then 2 zeros, and that violates the condition. So this is a contextual set. And you cannot expect of Eve to respect these conditions, because quantum outcome is that you'll have one either here or here, one either here or here, one and so on, no? And she can send in that way as well. So the possible resolution to this problem is that we change the way in which we do cryptography with contextual sets. In the sense when we have got a really complicated hypergraph like this one, and when we reduce it from a Kochen-Specker type, in which all hyperages have n vertices, to a non-Kochen-Specker contextual set like this one on the right, then we can assign a minimal number of ones to the hyperages and send that as a message. And you see that it's so complicated. The Eve doesn't have any chance, because we send it, and later on Alice informs Bob over a classical channel what is the classical assignment for this quantum output. And there are a large number of such assignments, and it is efficient, but perhaps it's not the way the companies would accept to use contextual sets for their communication. They are mostly fixed on BB84, even without Eve. So let us have a look at, so perhaps that's all overkill both. Let us have a look at the oblivious communication protocol. That can be set up, although it's a little bit too complicated to go into details here. We provided the details in our recent paper of this year. What's important is that the proposal can be formulated without respect to dimensions. So we can use it for any dimension, and it's more and more efficient the higher we go in a dimensional space. So here we have got some details. The fourth is Hadamard gates. That's very interesting. Recently there was a theorem which handles the so-called S-class of H Hadamard matrices, and as a result we have got a generation of the hypergraphs in even n-dimensional spaces. So why is it interesting? Because I found out that we can go the other way around. There are two things, but we can have a hypergraph to which we assign some vectors, for example with 0, 1, -1 components, and then we can go back to Hadamard matrices and determine their values in any dimension. The second thing is that can be rather simply shown that all these Hadamard hypergraphs have a star-like form, like this. So we find a coordinatization, this one, or this one, and we go back and we know what's the appropriate Hadamard gate. And finally, the stabilizer operation as an application is connected to what we started with. The set that Howard and others used to start the induction proof with is here. It can be filled into the full representation, because it means if you have got this representation of a pentagon, you can add these things, and when you add them you find out that it's a non-contextual set. But when you add such vertices to this set, you find out that it is a contextual set. And this contextual set then can be simplified, and you get much simpler set than this one we started with, and it means that we can have a much simpler stabilizer for the error correction. And we can go to and fro and simplify our results, and that's in connection with the last night talk that the quantum error correction is a hot topic and should be wishable. With that, I thank you for your attention.
Thank you very much for the presentation and the insight on these contextual concepts. So we have time for questions. So there was one question already, discussion. So maybe I start with one question, if I may.
Yeah.
So you mentioned some of the experiments that have been done, for example, with this angular momentum state.
Yes, yes.
But in principle, if you have one system where you have an arbitrarily large alphabet, so that you can produce orthogonal scales, I think that's a physical system where you can try to implement these contextual sets of states, or?
It depends on what you want of them.
Yeah.
Because in my opinion, if you want them for quantum communication in a cryptographical sense, then you cannot prevent Eve to just interfere with the communication, because Eve can simulate quantum outputs. Because what's actually essential for non-binary hypergraphs, Kochen-Specker-like hypergraphs, is that we have got a distinction between classical implementation of possible experiments and quantum implementation of possible experiments. The classical is the one in which all these conditions are satisfied, and quantum in which they are not. Yeah. But Eve doesn't care about that.
Yeah, I mean just for the physical resources that are required. So it's not required that you have this, like in a hyper entanglement, that you have the entanglement between different, like for example, polarization or angular momentum. So it could also be only one property of the state. Or for example, we do a lot of in time. So in time, you of course can subdivide time in arbitrarily many time bits.
Yeah,
and
yeah.
So if you have one string that you artificially divide it in like 100 time bits, and you can create any kind of maybe superposition or entanglement. So this would be a platform, right, to implement these states. If you can do the entanglement and maybe
yes. If you can design it in a very clever way, then it would be the same as, for example, if you were able to send atoms from one Stern-Gerlach to other to the next and so on, and in the end you can have only quantum go through, because classically you can't go through all the devices, but people have tried to make such a concatenated Stern-Gerlach devices. It's simply not feasible. I mean, theoretically you cannot make it. But in principle, you are right. Perhaps with the time sequencing, you can do that.
Okay.
Good. So for the application of stabilizers, you could take a very complicated stabilizer and simplify it to a simpler one in your last slide.
Yeah.
Is this a fundamental limit on
yes,
simplification already, or it can, in principle, be improved somehow?
Yes, that's a good point. If you have sets with all vertices in all hyperedges, that so-called Kochen-Specker hypergraphs, then you have got the lower limit, which is called a critical hypergraph, under which, if you remove any of the hyperedges, it stops being contextual. It doesn't work for non-Kochen-Specker contextual sets. You can go further and further down, and then each level you can check whether it's contextual or not. For example, this one is shown with the vertices that belong to only one hyperedge, because that's the hyperedge. No? This vertex, for example, 2 belongs to only this one, while 1 belongs to the green one and to the red one. When you remove all the gray ones, you have got much simpler structure. But I imposed a restriction of down reduction, because I wanted to have the simplest possible hypergraphs that do belong to a particular n-dimensional set by definition. Because if you remove that things, then you have got something that is not anymore obviously n-dimensional, like this one. If you remove all these things, it's two-dimensional, it's not anymore three-dimensional. But if you want to just make a reduction like this, there are many papers in physical review letters about this thing. I mean, they deal with two-dimensional, but they say it's in a three-dimensional space, which is a bit weird. No? So it's just an approach to keep all the vertices in at least one hyperedge, which is from that space. Now, of course, they are here. They are contextual no matter whether you take these gray vertices into account or not, as opposed to this thing. So I'm looking at the critical non-Kochen-Specker contextual sets in the sense that they keep their contextuality no matter whether you take the gray vertices into account or not.
Yeah, maybe a very basic question. What exactly is contextuality? Is it the same as entanglement?
No. The contextuality is just the difference between a classical assignment to definite outcomes to all possible ports within a gate and quantum measurement of such ports within a gate. When you go to a structure like this one, you see if you assign 1 to 1 here, then this, and this, and this, and this should be 0. And that means that this hyperedge has got just zeros. And that means you don't have an outcome. That's not possible in quantum situation, because if you mimic quantum outputs, you have to have an outcome. You have to have click on one of the ports, either here or here or here. And classically, such a request is violated in such a set. So it means it's contextual. When you do quantum measurements, then you have got 1/3, 1/3, 1/3 probability, and you always have got an output. So quantum measurements violate this restriction.
Okay, good. Yeah, thanks. Okay.
Okay. Thanks.